Now, almost all chemical reactions either absorb or release energy in the form of heat. So heat, we need to define our next term, heat is the transfer of thermal energy between two bodies that are at different temperatures. All right, now in chemistry, we're usually talking about heat absorbed or heat released when we're talking about energy changes. And so this area of chemistry that we're looking at now, this is called thermochemistry. And this is the study of heat changes in chemical reactions. Okay, now in order to talk about the energies of reactions, we have to get a couple more terms down. So there is something called system, and then something called surroundings. Okay, so when we refer to the system, this is referring to the specific part of the universe in which we're interested in. And the surroundings, this is the rest of the universe outside of the system. Okay. Now, there's three different ways that we can categorize a system. So it's possible that you could have an open system where you can exchange mass and energy. You could have a closed system where you can exchange energy but not mass. And you can have an isolated system where there's no exchange of energy or mass. Okay, so here's what it looks like. So think of this as like a pop bottle. So if I go get a bottle of pop from a soda machine, if I get that pop bottle before I open it up, it's a closed system. The cap is on it. I can't get any pop out of that bottle, but what I can do is influence the temperature. If I put this bottle in a refrigerator, I can keep it colder. If I put it in a freezer, I can make it much colder. If I leave the pop bottle up, it'll get warmer. Now, if I take the cap out, that's an open system. So I can drink pop out of the bottom. I'm going to lose mass from that bottle. It's also going to make sure, because I'm leaving pop bottle out, I can also transfer, make the pop bottle hotter. I can also make it colder if I put it back in the fridge. Likewise. Now, let's say instead of having a pop bottle, what if I had a cup of coffee and I put that cup of coffee inside a thermos, inside a travel mug? Here, I can't take anything out. I can't take any mass out. I can't even change the temperature. So putting the thermos inside a refrigerator or leaving it out is not going to change the temperature of the substance inside that thermos. So the bottle on the right, this is called an isolated system. A bottle with a cap on it, this is a closed system. And then the bottle open, this is an open system. Now, I have a note here that says, remember the hydrogen balloon reaction? And if we had the situation, if this was an in-person class and we were actually in a lab, this would be something I would try to do, where I would try to explode a hydrogen balloon. But for us, instead of looking at the hydrogen balloon, let's take a look back at history and look at the Hindenburg. Now, the Hindenburg was an airship that was built by Germany in the late 1920s, early 1930s. And whereas most airships used helium gas, which is very light, helium is a noble gas, so it's not going to react. At that time that Germany was building the Hindenburg, there was an embargo on helium, and the country that makes helium the most is the U.S. So we had placed an embargo on helium in the early 1930s. So when Germany was designing this airship, the only way to get this airship literally off the ground was to use another gas that was lighter than air, lighter than helium, but it was also cheaper than helium, and that gas was hydrogen. So the Germans built this airship that used hydrogen gas to lift the machine instead of helium. And as it sailed on its maiden voyage from Germany into New York, and on May 1937, the airship encountered an electrical storm over Lakehurst, New Jersey, as it was trying to land. And so here is the video here's a clip of the Hindenburg trying to land in 1937.
The ill-fated Hindenburg on her last flight sails over New York. These pictures, made from a Pathé News plane less than 4 hours before the tragedy, show the world's largest airship heading for Lakehurst, New Jersey. Over Newark's famous auto skyway, the airship was hailed by thousands who little dreamed it was their final glimpse of the Hindenburg. Inside the silver envelope are 16 separate gas bags, each filled with hydrogen, a highly inflammable gas. From the ground, you can see the forward control cabin from which the ship is operated. The windows along the side indicate the location of the passengers' quarters, in which many were carried to a flaming death. Approaching Lakehurst, the Hindenburg appeared a conquering giant of the skies, but she proved a puny plaything in the mighty grip of fate. It almost seemed as if fate had set the stage for the horrible tragedy. A graceful craft sailing serenely to her doom. For 3 hours, the dirigible circled the landing field at Lakehurst, New Jersey, dumping more water ballast than ever before in vain efforts to level off. Again she dumps ballast, and a nervous tension grips those who are watching, for this is something unusual. There goes more ballast, but the tail is settling in spite of all that has been dumped. A grim note of impending tragedy. Finally, the landing lines are dropped. These scenes were filmed by Pathé News cameraman William Deek, and you're about to see the pictures he got when the ship exploded. Those aboard leaping for life from a flaming inferno. The actual crash of the Hindenburg, an airship destroyed in less than half a minute. Rushing to the rescue, the heroes of the tragedy dash in, heedless of danger, to help the injured to safety, while others, beyond help, perish in the flames. The blazing aftermath reveals the extent of the disaster, an inferno which became a flaming tomb, a twisted mass of girders, the seared and scorched skeleton of what was once a mighty airship. The Hindenburg has gone. She represented man's latest attempt to conquer the Atlantic by air. Her tragedy will not halt the march of progress. From her ashes will arise the knowledge, from her fate the lesson that will lead to a greater and a better means of mastering the air. If so, her dead will not have died in vain.
That's an extremely sad situation, but the reason why I'm bringing it up here is that it was one of the most simple chemical reactions where you're taking hydrogen gas, reacting it with oxygen gas, and you form water. That's it. That's it. Now, this video doesn't hint at it, but scientists and engineers even today are still trying to answer the questions of why did the Hindenburg go up like that? What was causing that? And there's still a couple answers. There's still a couple ways of looking at this. One way was that there had to be some sabotage, some sort of espionage on board. Someone had planted a bomb, and the bomb went off near one of the fuel cells, and that's what caused the hydrogen leaks, or caused the explosion. The other thing to keep in mind is that, and most scientists have agreed that this is the most plausible, is that it was coming in trying to dock during an electrical storm. In certain interviews with people that were on the scene, there were cloud-to-cloud lightning. So it's possible that while the Hindenburg was trying to land, that there was some cloud-to-cloud lightning. It was definitely a very charged atmosphere in that. You've got this huge airship that was covered with aluminum foil or an aluminum skin going through these clouds. And anytime you're creating friction, if you rub your feet across carpet and your feet are have socks on them, you're creating friction. At some point, you got to discharge that electrical buildup. And so that was the way that scientists are trying to explain why the Hindenburg went up like this. But this brings up, this really connects to where we're talking about. So we saw that this was, the Hindenburg explosion was an explosion. This released a lot of heat, a lot of energy really quickly. And anytime we see that, where a reaction is releasing energy very quickly, this is called an exothermic reaction. So an exothermic reaction, this transfers thermal energy from the system to the surroundings. From the system to the surroundings. In other words, it's releasing energy. The other type of reaction is an endothermic reaction. In an endothermic reaction, it transfers thermal energy, this time from the surroundings to the system. So this absorbs energy. Now that we've talked about the different types of systems, we've talked about exothermic, we talked about endothermic reactions, we talked about the types of energy, now we're ready to talk about the first law of thermodynamics, which is what we're going to talk about in the next video.